Good morning. We will continue with the next topic, reflection coefficient. We will start with the previous equation, that is Vs of t or Vs of z comma t is equal to V plus exponential of e raised to minus gamma z plus V minus exponential of gamma z. Similarly, Is of t equals I plus exponential minus gamma z plus I minus exponential plus gamma z. Okay. Now this is a typical transmission line. This is the generator side. This is the load side. If the electromagnetic wave is moving in this direction, then you can see the wave is moving towards the load, and if the wave is moving in this direction, we can say it is moving towards the generator. Okay. And this point is taken as Z. Now we know what is Z0. Z0 is equal to V plus by I minus, or minus Z0 is equal to V minus by I minus. Similarly, we know what is Is of t. It is V plus by Z0 exponential minus gamma Z minus V minus Z0 e plus gamma Z, which we already derived. Now at Z equal to 0, we know what is Z. Z is at Z equals 0, Z is equal to V by I. So here in this expression you can substitute Z equal to 0, and in this expression you can substitute Z equal to 0. So finally you will get what? Z0 into V plus plus V minus by V plus minus V minus. Okay. Now from the picture at Z equal to 0, the impedance is ZL, right? That is, here you can see Z is equal to 0 is this point. Okay, because here we are dealing with reflection coefficient. So what do you mean by reflection coefficient? It is a portion of electromagnetic wave which is getting reflected. So from where does the electromagnetic wave get reflected? It will get reflected from the load side, right? Initially the electromagnetic wave will be moving from source to the load. Okay, suppose this is a load and this is a source. It will be moving from source to the load, and once it reaches the load, it will get reflected back. So the reflection starts from the load side. That is why in this picture Z equal to 0 is the end towards the load side. Okay, so here from the picture at Z equal to 0, the impedance is ZL. Okay, the impedance is ZL. So what happens to the above equation? Z. So this Z can be replaced as ZL. So again write ZL is equal to Z0 into V plus plus V minus by V plus minus V minus. Okay. So the next step, what I have done is, yes, V plus is taken outside. So now the expression looks like this. Okay. So now here listen, we are dealing with two terms, that is V plus and V minus in last few videos. So actually what is this V plus and V minus? V plus, it is the amplitude of the wave traveling in the forward direction, that is the incident field, and V minus is the amplitude of the wave traveling in the backward direction, that is your reflected wave, right? So the reflection coefficient tau L, okay, L is used to represent a transmission line. Okay, that's all. Tau L is a ratio of V minus by V plus. V minus is your reflection amplitude of your reflected wave, and V plus is the amplitude of your incident wave. So in this expression, again write what is ZL. ZL is equal to what? This V plus and V plus get cancelled. So 1 plus Instead of V minus by V plus, you can write tau L. Similarly, here also tau L. So finally, ZL is equal to 1 plus tau L by 1 minus tau L into Z naught, which is your load impedance in terms of reflection coefficient. From that, you can find out the reflection coefficient tau L in terms of impedance as ZL minus Z naught by ZL plus Z naught. So this is a formula for reflection coefficient in a transmission line. Similarly, you can find out the transmission coefficient of transmission line as transmission coefficient is equal to 2ZL by ZL plus Z naught, and this derivation you can do as self-study. Now, if ZL is equal to Z naught, in this expression you just assume that if ZL is equal to Z naught, what happens to tau? Becomes 0, right? That means there will be no reflection when ZL is equal to Z naught. That means the impedance, that is the load impedance ZL, is matched with the characteristic impedance. When the load impedance is matched with the characteristic impedance, there will be maximum power transfer. So I repeat, if ZL is equal to Z naught, this factor will be 0. That means there is no reflection. So here this load impedance is matched with the characteristic impedance such that maximum power transfer happens. And that's all under reflection coefficient. Next we will see in term voltage standing wave ratio VSWR. The voltage standing wave ratio VSWR is given by the formula V max by V min, which is equal to 1 plus tau L by 1 minus tau L in terms of your reflection coefficient. Then this VSWR is often represented using the alphabet capital S. So you know how standing wave is formed. That is, when the signal gets incident, when the electromagnetic wave get incident, what happens is when it reaches a load impedance, it will get reflected back. Okay. Sometimes the reflected wave and the incident wave will be in phase. In some cases, the reflected wave and incident wave will be out of phase. Okay. And you know, V max will be this portion and V min will be this portion. So this is the expression of VSWR in terms of the amplitude, maximum and minimum amplitude, and this one in terms of reflection coefficient. Now we will see different conditions of a voltage standing wave ratio. Now suppose your load side is short circuited, that is, this is your source and this is your load. It is short circuited. That means ZL is equal to 0. In that case, your tau L, the reflection coefficient, will be -1 and voltage standing wave ratio will be infinity. You can substitute the condition ZL is equal to 0 in this expression, and similarly you will get a value for tau L, and that tau L can be substituted here to find out VSWR. Okay. So finally you will get tau is equal to -1 and VSWR is equal to infinity, and we will get the input impedance of the short circuited line, that is Zn is equal to ZSC. SC represent short circuit, which is equal to JZ0 tan beta L. Okay. This is the expression for input impedance of a short circuited transmission line. Now here the impedance in a short circuit line, the impedance will be purely reactive. So the incident wave is reflected with equal amplitude and phase reversal. So here in this case, if the load impedance is short circuited, then the reflected wave and the incident wave and reflected wave will be having same amplitude, but they will be out of phase. So this is how the standing wave appears to be in a short circuited transmission line. Similarly, coming to open circuited line, your ZL is infinity. That means it will look something like this. This is your ZS and this is your ZL. That is, it will be open circuited. So in that case, your tau will be 1 and S will be infinity. You can substitute the condition in tau, and finally the tau can be substituted in S. Okay. And the Z input impedance is equal to ZOC, which is OC represents your open circuit, which will be equal to Z0 by J tan beta L, which is equal to minus J Z0 cot beta L. This will be your input impedance for open circuit line. And this is a relation connecting ZSC, ZOC, that is Z0, that is your characteristic impedance, will be the square root of the product of ZSC and ZOC. Okay, and this condition is important. And now in this case, if the load is open circuited, then what happens is the incident wave and the reflected wave will be having same amplitude without any phase change. So if it is short circuit, they will be having same amplitude with the phase change, and if it is an open circuit, they will be having same amplitude without a phase change. And these are the diagrams of short circuit line and open circuit line for different length. Suppose if your length L is less than lambda by 4, then the short circuit line acts as an inductor, and if the L length of your transmission line is between lambda by 4 and lambda by 2, then it acts as a capacitor. Similarly, if L is equal to lambda by 4, your output impedance acts as a combination of inductance and capacitance. Similarly, here you can see the case of open circuit line, if L is less than lambda by 4, then your load acts as a capacitor. Similarly, if L is equal to lambda by 4, then the load acts as a series combination of inductor and capacitance. And if L is between lambda by 4 and lambda by 2, then the open circuit load is equivalent to an inductor. And that's all in this section, and thank you.